Welcome back, everybody. This next hypothesis test is going to be an upper tail test. And again, we're going to assume that the population standard deviation is unknown, and because of that, we're going to conduct what's called a t-test. This is how it reads. The National Health Statistics Reports described a study in which a sample of 361-year-old baby boys was weighed. Their mean weight was 25.5 pounds with a standard deviation weight of 5.3 pounds. A pediatrician claims that the mean weight of 1-year-old boys is greater than 25 pounds. Do the data provide convincing evidence that the pediatrician's claim is true? Test at the 1% level of significance and show all 5 steps. Okay, so step number 1 is we're going to clearly establish the null and alternative hypotheses that are going to be tested here. Now, a hint here as to how we establish our hypotheses is in this sentence here. It says a pediatrician claims that the mean weight of 1-year-old boys is greater than 25 pounds. So greater than. Remember, our alternative hypothesis can only take on one of 3 symbols: not equal to, greater than, or less than. Okay, and since the claim is saying greater than 25 pounds, that would be our alternative hypothesis statement. So therefore, that would say, the alternative hypothesis statement would say that the mean weight is greater than 25 pounds. Therefore, by default, the null hypothesis statement has to say, therefore, that the mean weight is equal to 25 pounds. Okay. So these are the hypotheses we're going to test. And step number 2 is establishing the the level of significance that we're going to test at. And notice we are going to test at 1%. So that is going to be what alpha is set at, our level of significance. Step number 3 is computing our test statistic value. And again, that is computed by using sample evidence. And the formula we use is this T formula, which says T is going to be equal to the sample mean minus the purported population mean under the null, divided by the estimated standard error, which is a sample standard deviation divided by the square root of the sample size. Now, what's our sample mean? Well, of 361-year-old baby boys who were randomly surveyed, their mean weight was 25.5, that's X bar. Subtracting off the purported mean of the population under the null statement, which is 25 pounds. Make sure you can close that inside parentheses, divided by the estimated standard error. So the standard deviation of our sample is 5.3 pounds, divided by the square root of the sample size, and the sample size is 360 babies were randomly surveyed. After dialing this up on your calculator, you should get a test statistic which is approximately about 1.790. Step number 4 now is clearly establishing the rejection and acceptance region to make a determination as to what we're going to do with our hypotheses. Please, when you do step number 4 using this manual approach, this critical value method, make sure you always draw a picture of the probability distribution, in this case the student t distribution, which, like the normal distribution, is symmetric and bell-shaped. Now this is going to be an upper tail test because our alternative hypothesis statement is a greater than symbol, and greater than means upper tail test. That means the rejection region is going to be only in the upper tail of the student t distribution. And the size of this upper tail rejection region here is going to be determined by the value that we set for alpha, our level of significance, in step 2, which is 0.01. So this area in the upper tail of the student t distribution is going to be 0.01. Notice we don't take half of this value like we did in the previous problem when we were doing a two-tail test. This is only a one-tail test or an upper tail test. Now to find the critical t value that separates the rejection from the other region, which is the do not reject the null hypothesis region, we're going to have to use our inverse t function on our calculator. But notice your inverse t function on your calculator requires that you always type in the area to the left of the t value you wish to find. Well, our t-value has area to the right of it, which is 0.01. And so what we're going to type in is we're going to type in 0.01, but when we do so, we're going to get a negative t-value, but we'll just drop the sign, the negative sign, and just report it as the positive value uh, due to symmetry of this curve. So type in 0.01, and the degrees of freedom is going to be the sample size minus 1. Our sample size was 360, so 360 minus 1 is 359. That'll be your degrees of freedom. All right, when you dial this up in your calculator, you're going to get approximately about 2.364. Now again, your value is going to be a little bit off from this because I used a table to look up my t-value, because again, my TI-83 does not have the inverse t function. So don't worry if we're off a little bit, as long as it's ballparkish. That's not going to change your decision regarding hypotheses anyways. Okay, so 2.364 is that critical t-value that separates the upper tail rejection region from the rest of the curve, which is the do not reject the null hypothesis region. Now, to make a decision regarding our hypotheses, we look at our test statistic, which is 1.790, computed back in step 3. And we ask ourselves, where is 1.790 in relation to our cutoff value, or critical t-value of 2.364? Notice 1.790 is less than 2.364, and so therefore our test statistic falls safely in the do not reject region. Now, what was the claim for this test here? Notice it says, do the data provide convincing evidence that the pediatrician's claim is true? Well, the claim was that the mean population weight of all 1-year-old baby boys is greater than 25 pounds. So the claim is going to be the alternative hypothesis statement. Well, unfortunately, we're not able to reject the null hypothesis. And for that reason, the claim is not being supported by sample evidence here. And so therefore, our conclusion regarding this test is this. We would say that sample evidence is not strong enough to support the claim that the population mean weight of all 1-year-old boys is greater than 25 pounds. So sample evidence is just not showing that claim to be true. So this concludes an example of an upper tail t-test for an unknown population mean.